All right, guys, in the last video, we kind of rushed through this whole example problem. We got to a point, though, where we did kind of draw a possibility of this particular type of molecule that could give rise to this infrared or this mass spectrum. And then up here is a bunch of scribble that happened on the screen, and it was chopping all of my organization of that molecule around. So I just kind of want to go back and I just want to review where we're getting that second piece. So almost just imagine that this just didn't even happen. Okay, so with that said, this was one of our possibilities, right? It was a 4-carbon chain with a double bond O and an H after the end. So I'm going to write that down here. So 1, 2, 3, and then that carbon in the carbonyl makes the 4th carbon. So that's going to be a double bond O with an H. But we said that's not the only way that we could draw this structure. Okay, so I'm going to go back and I'm going to do the aldehyde group. Off of this aldehyde, I'm going to put, look, we got 3 carbons to play around with. Well, there's 2. If I put the 3rd one here, that's the same structure as what we did in the beginning, so it can't go there. And the other option to order this guy up is to put the carbon there. All right, so I'm going to now go in and kind of fill in all of the hydrogens that are needed for that particular molecule. So there we go. There's our 2 choices, and we've got to figure out which one of these compounds would actually give rise to this infrared and this mass spectrum. Now, the infrareds are not going to tell us any more information. It only told us that a aldehyde was present, and that was it. So as far as the infrared goes, I can't really look at that anymore here. In a database system, I could on a computer. But as far as me interpreting the data, it's not going to tell me anything else. We're done with the infrared, no more of it. All right, so then I'm going to come down here and look at the MS. It looks like the MS has a M or a parent peak at around 72. That's how we determined how many number of carbons and hydrogens there were that were present on the aldehyde. That's how we knew how to stop. Now I need to take a look at the fragmentation pattern. How is this molecule going to fragment, and what's going to happen? Is there a way that I can tell a difference between the two when it goes through this mass spectrum or mass spectrometer? So maybe one of the ways that I could look at this is take a look at the base peak. This base peak here, if I kind of just come down to the bottom of the M to Z ratio, it looks like it's going to be about a 44. That's the tallest peak. This looks also like a fragment. Maybe I can identify it. Maybe I can't, but I can at least label it. So here's 60, and there's 59 and 58, and maybe 57. Maybe over here's another one. I can label this one. This is 25, 26, and 27. And then 28 and 29, that's going to be here. As far as this one, that's a pretty tall one too, right? If I track that one down, that's going to be a 41. And then here is going to be a 43. So I've just labeled these peaks. I maybe could get a reason of how to get these. Maybe I won't. Who knows? That's to figure out. But I can at least identify some of the peaks that are present. All right, so now I'm going to go back and we're going to think about maybe how this thing would break apart into its pieces. Now, look, this is an aldehyde. We've talked about ketones. We've talked about how ketones will break apart. And we said that if we have a C double bond O with a carbon on each end, we would look at the alpha carbons and we could kind of cleave at those positions, right? Well, we didn't really talk about aldehydes at the time. They're similar, but they're not the same. So could I maybe use this as a guide to figure out what we have and what we don't have? Well, let's see. Let's just apply the theory of ketones to those of an aldehyde. So here is the carbonyl band, and we said that beside of that is the alpha carbon. So let's just pretend like this molecule could possibly cleave at this location. If it does, it's going to take those electrons inward, and we're going to get a CH2 carbon triple bond now to an oxygen with a hydrogen that carries with it a positive charge. All right, so let's go through and do a fragment weight. We have 12 and 2, 12, 16, and 1. And this gives me a 43. If I go back to the mass spectrum, I actually see a 43 that's present. Right there it is. Okay, so that makes me feel a little bit better. I'm getting close, right? So if we take a look at this molecule over here, what if we apply the same principle? Here is my carbonyl group. Here's the alpha carbon. The alpha carbon could make the decision to cleave, and that's what it does. And it doesn't really matter which one it cleaves. It could cleave the one to the left or one at the bottom, because it's going to give me the same fragment. What I have left over is a CH3 group, a CH, a C, now triple bond O with a positive group, and a hydrogen. So I'm going to come through and I'm going to do that fragment weight. 12 and 3, 12 and 1, 12, 16, and 1 gives me a 57. So if it cleaves here, it gives me a 57. There's the first choice. If it cleaves here, it gives me a 57. There's the second choice. As far as the alpha carbon cleavage, though, that's it, people. We can't get anything else. As far as the alpha cleavage over here, that's it. We can't get anything else other than the 43. So if I use the alpha carbon, the problem is that I see 57 listed on the chart. I also see 43 listed on the chart with 44 as a base peak. So there's got to be more to it than this. All right, well, let's kind of start applying the rules that we've learned about functional groups. And we said, because this really isn't a ketone, right? We were just applying what we learned about ketones to aldehydes to see if we could get some numbers that show up on the chart, and we did. So what if the functional group completely cleaves off, just goes away? We kind of saw that with bromine and chlorine, right? We chopped it off and removed it. So what if we just completely cut the bond at that location? Well, what we would end up with is that functional group would go away. 12 and 3, 12 and 2, 12 and 2 would be left behind, and look, we get 43 again. If this gets cleaved, 12 and 3, 12 and 1, 12 and 3 gives me a 43. Oh, look, 57 and 43. Nowhere have I gotten a 57 on this yet. So this would probably lead me to believe that this MS in infrared is actually this ketone. And the reason is because I can get a 57 from this fragment, and nowhere yet have I been able to get a 57 over here. So there we've identified the aldehyde. We can probably feel good about what we've just done, hopefully. And in the next video, we'll move on to our next example.